Even before we built our first crude spaceships, Alpha Centauri has loomed large in our imagination as the gateway to the stars. It's the closest system, the one every science fiction writer sets their sights on. In our recent episode, the first interstellar colony mission, we considered the Alpha Centauri system, along with Proxima Centauri, as high probability candidates for first missions. While it may be our first, it certainly won't be our last. There are, after all, a few 100 billion stars in this galaxy alone. Beyond Alpha Centauri lies an entire neighborhood of stars: dim red dwarfs, ancient suns, white dwarfs cooling in the dark, and even the faint glow of failed stars that never quite ignited. Within just a dozen light years, there are more than a dozen systems. Stretching out to 25 light years, we find a tapestry of K, G, and F-type stars that could sustain human industry and offer decent terraforming prospects. And even stars far smaller than our own, such as red dwarfs, at least provide the raw materials for civilization. None of these systems are perfect, and in fact most of them would make poor science fiction backdrops. No lush Earth twins with twin moons, no guaranteed second Edens. What they offer instead are challenges: flare stars, tidally locked planets, debris belts and dead companions, but also opportunities for habitats, mining, and energy collection. The reality is that humanity may find more promise in building our own homes than searching for ready-made ones. So today we'll look past Alpha Centauri to the rest of our local bubble and ask, if we can reach Proxima, Bernard's star, and Tau Ceti, what comes next? And which of our stellar neighbors might one day fly the first flags of humanity beyond Sol? But before we get to that, let us also remember that these are entire star systems, many of which have not only more than one planet in them, but more than one star. There are more stars within 25 light years of Earth than there are nations on Earth, and we can share the same planet, then tiny colonies of a few thousand should be able to share one with each other, and certainly can share the same star system. Thus, we should not assume traveling to a star means claiming it in its entirety for a given nation. I have a suspicion that the next couple of decades will see borders on this planet shift in ways they mostly have not since the aftermath of World War II, and if they do, I don't think it will be a move towards more unified, bigger states. In science fiction, it tends to be ubiquitous for Earth to fall under one single government in the future, and even more so that the planets we settle would be unified, but I doubt both, and I think that's a key piece to keep in mind as we begin looking at the local stellar neighborhood. Space is immense, and scattered small communities of pioneers are not likely to have unified motivations or any special urge to remain unified with neighboring settlements or distant homelands. The immediate neighborhood. As mentioned, there are a few hundred stars within 25 light years, and more like 20,000 if we expand it out to 100 light years. Loosely speaking, every time you double the width of your zone, you're getting 2 cubed or 8 times more stars, systems, and planets in it. But that is only approximate, and things are slightly more sparse in the 12 light years closest to us. Whenever drawing spheres like this, it is also important to remember that most of the stars are on the outer region of that shell, not evenly distributed. Half the systems should be in the outer fifth of the sphere, because half the volume of a sphere is in the last 20.6% of its radius. So of those 20,000 stars within 100 light years of us, half of them, 10,000, are at 80 light years or more. Within just an eighth of that distance, 12.5 light years of Earth, our local neighborhood already includes about 20 star systems. Closest of all is the Alpha Centauri triple system, the sun-like stars Alpha Centauri A and B, and their dim red companion Proxima Centauri, with its trio or so of known planets. Next is Bernard's star, a fast-moving red dwarf of possible super-Earth. And that's it for everything within 6 light years, and we looked at those options in more detail in the first interstellar colony mission episode I mentioned. After that we have Schultz's star, a red and brown dwarf binary pair, followed by Wolf 359, one of the faintest stars visible from Earth and where we disastrously battled the Borg in Star Trek. A little farther lies Lalanda 21185, another red dwarf with at least 2 suspected planets. We now have a number of red dwarf systems, and besides Alpha Centauri, that's all the stars we've got in this radius, red dwarfs. That is not unusual, they are the supermajority of stars, and most of the remainder are K-type orange dwarfs. Depending on how we count them, Yellow dwarfs like our Sun and brighter stars make up less than 10% of available stars, much less if we include borderline cases of ultra-dim red dwarfs and the largest brown dwarfs. Where you settle depends a lot on your technology, as if you got decently efficient fusion reactors, you are not just adding in brown dwarfs as possible systems, you're adding any rogue gas giant or even planets with a decent supply of volatiles, as water, ammonia, and methane are all full of hydrogen and thus deuterium, our go-to fusion fuel. Interstellar rogue planets won't be short on helium in most cases either, should we get aneutronic helium-3 fusion working. There could be several hundred such bodies within this radius, all floating around by themselves or with a few moons, and all entirely viable settlement candidates, and ones that will probably view themselves as independent systems, islands, not continents, but not footnotes either. Odds are good that an actual star will always be a preferred target though, whatever its color, because they do fusion for free, and mirrors to concentrate their light are likely to be cheaper to build and maintain than an equal amount of reactor. Nor are we limited to their natural light spectrum. All stars are white light sources, but they have a peak color. Amusingly, for our yellow sun, that's actually blue-green. For a lot of red dwarfs, the light they give off is more like a classic incandescent bulb or warm bulb, but their peak is usually in the infrared, and most people want more sun-like lighting. Amusingly, this isn't likely to be that hard to change. It is very unlikely that any of the planets in the habitable zones of the nearby stars we discussed so far would avoid tidal locking, which would mean permanent day on one side and endless night on the other. This can be addressed with orbital mirrors and shades, or with reflectors positioned at the planet's L1 Lagrange point. But even if they were fortunate enough to find a world that still rotates on something like a 24 to 26 hour cycle, its sunlight wouldn't look much like Earth's. The spectrum would be very heavy in infrared and weak in visible light, especially in blue and violet ranges. To compensate, you might deploy mirrors tuned to reflect visible light, particularly blues, while adding shades or filters to cut back the excess infrared. The same approach works on space habitats that we can build pretty much anywhere there's some rocks and ice balls to harvest, which is probably 99% of star systems. You have to create or reflect all your light into those anyway, so you might as well screen it and use the other wavelengths for generating power while giving yourself your preferred spectrum, which will change over the course of the day and year anyway. I should also note that with the use of a vast array of mirrors, approaching Dyson-level coverage, you could position reflectors over a star's north and south poles to bounce light back down, effectively warming its surface and increasing its output of visible light. We call this star boosting, and also has the side effect of widening the star's equatorial habitable zone, where planets are more likely to orbit. It is a massive undertaking, but not necessarily one that requires exotic technology. You can use other methods to weaken stars as well, but there are even fewer larger stars that are yellow suns like ours, so this isn't a big concern. Indeed, the first star significantly brighter than our Sun, Sirius A, is our next system, a blazing A-type primary paired with a dense white dwarf companion. Not far beyond lies Procyon, another bright star with a white dwarf partner. Amusingly, in nearly every such pairing, the smaller white dwarf was once the heavyweight of the system, outmassing its companion before shedding nearly half its mass in the course of becoming a red giant, then a white dwarf. Procyon A itself is just entering that transition, currently a subgiant, the stage between main sequence and red giant. These white dwarfs, now the faint footnotes of their system, were once the kings. It's also tempting to think of such systems as ancient, but in truth, Procyon is less than half the age of our Sun, while the Sirius system is only a fraction as old. Sirius B likely collapsed into a white dwarf when dinosaurs still ruled the Earth. Neither Sirius nor Procyon offers a great option for a classically habitable planet. Sirius B follows a long elliptical orbit that brings us as close as 8 AU to Sirius A, about 8 times Earth's distance from the Sun. Any planet in that region would likely have been heavily perturbed, and likely flash-fried when Sirius B spun into a red giant 100 million years ago. Sirius A itself is the brightest star in our night sky and about 25 times as luminous as the Sun, which puts its habitable zone centered around 5 AU, 5 times wider than ours. In contrast, Sirius B, now shining at just 2.5% of the Sun's luminosity, would have a habitable zone only about 1/6 of the Earth's distance from the Sun. Ironically, a stable Earth-like planet is probably more plausible around the white dwarf than around its blazing sibling, though any such world would have had a violent past. Procyon is a little more forgiving. Its two stars stay farther apart, with the closest approach about 9 AU. Procyon A is about 7 times as bright as the Sun, placing its habitable zone near 2.6 AU. Still, both systems are shaped by the disruptive presence of white dwarfs. As we've explored in other episodes about red and white dwarfs, settlement here is far more likely to focus on asteroids and deep space habitats than on planets. Stars more massive than about 30% of the Sun's mass eventually swell into red giants, and nearly all the white dwarfs we see today began as stars larger than our Sun, which would have roasted their inner systems. Volatiles on nearby worlds and even the Kuiper Belt-like zones would be stripped away under the glare of a giant hundreds of times brighter than the Sun. Some may later be restored when the outer layers are shed as a planetary nebula, but much will be lost. These systems may prove decent mining sites, with some leftover debris disk still clinging to them, but they are poor candidates for early planetary settlement. Beyond this range, we also find the quiet Ross 128 with its planet Ross 128b, and Luton's star with 2 confirmed super-Earths, including a potentially habitable Luton B. They are red dwarfs, so we won't repeat the approaches to getting them settled. The orange K-dwarf Epsilon Eridani has 1 confirmed gas giant with a possible second one and 2 debris disks, while Tau Ceti, a near-solar twin, hosts multiple candidate planets. Beyond these better-known names are a host of red and orange dwarf multiples: 61 Cygni, Struve 2398, Kruger 60, Groombridge 34, Lacaille 9352, and Captain Star. Even fainter are the triples of EZ Aquarii and Luton 726-8, better known as the flare star UV Ceti. Teagarden Star rounds out the list, one of the smallest known red dwarfs with 2 candidate planets. All told, within 12.5 light-years of Earth, we already have some 40 stars, white dwarfs and brown dwarfs, more than enough to keep early interstellar explorers busy. Expanding the range, notable K, G, and F stars in 25 light-years. There's not many, if any, ideal classically colonizable star systems inside this range, but if we push out to 25 light-years, that rises sharply. As mentioned, we've got some borderline cases just inside the original 12 light-year bubble, but let's focus only on these nearer Sun cases going forward and work our way out. At just over 10 light-years away again is Epsilon Eridani, an orange K2 dwarf. It's a young and active star surrounded by 2 debris disks and hosting at least 1 confirmed gas giant. A long favorite in science fiction, it's also one of the more promising nearby settlements for eventual settlement, and probably the most valuable or at least desirable after Alpha Centauri itself. A little farther out, at 11.4 light-years, we find 2 famous pairs. 61 Cygni A and B are both K-type dwarfs, an orange double that has fascinated astronomers since the 19th century for its large proper motion. Both are variable stars, shifting brightness over time. A is about 15% as bright as our Sun, B is even dimmer at 9.7%, but is a flare star, making it suboptimal for any classic habitable planet, though you can use Lagrange point electromagnets to deflect away excess solar wind from any planet, powered by the star Bombardier. They are far enough apart that either could host its own habitable zone planetary system. No planets have been spotted yet, but they are good basic indicators. While there is some debate about it, they are probably older than us too, by over 1 billion years, so not only might they be good settlement targets, they might already have life. At 11.8 light-years we encounter Epsilon Indi, another K-type dwarf accompanied by a pair of brown dwarfs. This system is particularly interesting as one of the closest brown dwarf pairs, offering a look at objects bridging the gap between stars and giant planets. Close behind it at 11.9 light-years is Tau Ceti, a near twin of the Sun. It hosts several candidate super-Earths and a massive debris disk, making one of the most tempting targets for study and perhaps even eventual colonization, especially as amazing feedstock for building habitats. Beyond that dozen light-years, at 16.7 light-years, we meet Altair, a bright A-type star. Altair spins so rapidly that it bulges at its equator, giving it a distinctive profile and making it a notable oddity among nearer bright stars. It's about 10 times brighter than Sol, so has a habitable zone 3 times wider than ours. It's actually under 100 million years old, so has a lot of life left to it, even given its brighter and short-lived nature, probably a good billion years. That's not much on astronomical timelines, but it's thousands of times longer than human civilization has been around, even in generous estimates, and could easily have tons of planets and even thousands of decent minor planets to settle. So I think it might be less obviously desirable than the near suns we mentioned, but as an A7, it's just a bit bigger and brighter than our main range of discussion, and may be much more useful than them. Pushing nearly 19 light-years out, Sigma Draconis, a G9 dwarf, offers a quiet, sun-like star with high stability and a long life expectancy, while at 19.9 light-years, Delta Pavonis, a G8 dwarf, stands out as one of the closest near-solar analogs and a favorite candidate in exoplanet studies. At 20 light-years, we find 82 Eridani, a G6 star with suspected planets, yet another member of our extended solar neighborhood that might serve as a stepping stone for human expansion. Finally, on the edge of our 25 light-year survey, we come to Beta Hydrae, a G2 subgiant about 24 light-years away, and Fomalhaut, 25 light-years distant, a bright A-type star surrounded by a striking debris disk. Both are fascinating in their own right, though they represent very different stages in stellar evolution. As we imagine journeys beyond Alpha Centauri, it's worth asking who, or what, will actually build those starships. That's the question behind my new Nebula exclusive episode, Autonomous Space Industry, when AI and robots run the economy, where we explore how machines could build the next great wave of human civilization, from orbit to interstellar space, faster than we ever could alone. And when you're ready for something closer to home, SCAV on Nebula offers another side of human genius. Every year, the University of Chicago dives into a 4-day, 20-page-long scavenger hunt that turns the campus into a whirlwind of fun, science, and sleep-deprived creativity. SCAV follows 3 top teams as they race through the madness. It's hilarious, heartwarming, and pure energy. Nebula is home to many fascinating originals like SCAV you won't find anywhere else. It's also where every episode of SFAA premieres days before coming out on YouTube and elsewhere, and without any ads or sponsor reads like this one. Get a lifetime membership, normally $500 for just $300, by using my link go.nebula.tv/IsaacArthur and unlock everything forever, or get an annual plan for 40% off, $36 a year. That's 12 months for the price of 7. Scan the QR code or click the link below to start watching exclusive content like Autonomous Space Industry and SCAV. Even more. So that's everything prominent within 25 light-years, and again we got a few hundred stars in this range, and probably several thousand interstellar brown dwarfs and gas giants that could be considered their own systems if we ever get fusion working usefully. Indeed, as mentioned, you can probably start treating any ice ball big enough to build and support an O'Neill cylinder as one, given that could house 1 million people and reasonably viable as an independent nation. You could view anything in a star's hillsphere as part of that system. That's the region where that star's gravity dominates and is typically around halfway to the next star. Alternatively, you might just put it as exactly the half point between stars, but realistically, anything much beyond 100 AU is deemed dubious. That's well past Pluto and the Kuiper Belt, and still a few thousand times farther to Alpha Centauri. If any interstellar habitat chose to view itself as an independent system, if it had 100 AU or more to itself, and you could then have a few trillion such sectors inside this 25 light-year bubble we've been looking at. Even if we expanded that to be 100,000 AU, the outer edge of the Oort cloud, you still have a few thousand such sectors, and I can almost guarantee the vast majority of those will either have some decent-sized rogue body in them, or be strategically valuable enough that someone plants a habitat there and sends it the raw materials it needs to sustain itself. It's a bit ironic that fusion both makes this possible and makes it possible to get to other stars without needing all those relay points in between. If we remain limited to fission as our power source, your travel times are probably maxed out at 5% of light speed, at least if you've been able to settle those areas deep enough to be able to build big infrastructure like interstellar laser arrays, and honestly even 5% is a bit much for fission. Don't assume you can't do these relays and way stations with fission either. As we noted in the first Interstellar Colony mission episode, a Stanford Torus scale habitat with around 10,000 people can live fairly energy lavish and grow their own food on 20 to 30 tons of uranium or thorium a year. There's a few 100 billion tons of them in our asteroid belt, probably, that would fuel such a station for 10 billion years, or 1,000 of them for 10 million years. Plenty of time to perfect fusion or something else. And mass-wise, the whole asteroid belt is a lot smaller than our own moon, let alone all planets or all the planets, moons, and asteroids in that 25 light-year zone. So fusion would be nice, but fission still works. Settlement timelines. Speaking of time, your settlement timeline obviously can't be any shorter than your ships can travel. If you can manage 10% of the light speed to Alpha Centauri, that's about 43 years in transit. If 1% is your maximum speed, then a 25 light-year trip to Beta Hydrae, or other outer targets in the survey, is roughly 2,500 years. I tend to use 10% in a lot of our episodes, both because it's a nice round number and because I assume we are using large ships and fleets pushed partway to speed by beam arrays and slowed partway by solar sails and mag sails, and that's assuming you can't get a beam array working with your Vanguard, which I think you can. Indeed, I often assume the Vanguard of the colony fleet is an automated ship packed with mirrors, solar panels, and giant laser emitters that unfolds on the outskirts of a system and slows using the outward pressure of sunlight and the solar wind. It either parks around that star, or at least slows enough to run its beam for a while and push a twin a bit further behind. Rinse and repeat until you've built a pushing beam array in orbit of that star. That array then helps slow the rest of the fleet, which are also using hydrogen bombs or fusion drives for braking. And when I say laser, I really mean any particle or photon beam. A pushing system might fire charged hydrogen for magnetic deflection, or even neutral atoms the ship can scoop, shed momentum to, and then expel as propellant. Such braking maneuvers work far better on the brighter stars, which may then become your first natural beachheads as we move outward. In all cases, I am optimistic we can at least reach 5% of light speed. Long trip for a single Stanford Taurus, 20 million ton class vessel, but it's debatable if an O'Neill class ship would be preferable to say a dozen Stanford class ones, even if the big cylinder offers more room. Redundancy is handy, and quantity has a quality all of its own. Multiple ships also gives you more initial settlements ready on arrival, able to disperse to various planets and more interesting moons in the system. You may notice I'm not including acceleration and deceleration times. At these modest speeds over these long distances, they add proportionally little, perhaps a year or so. I am also not including construction time, which does likely fall more than a year. Even if you could build faster, you'd probably choose to build more in parallel. Nor am I counting time for a colony to settle in and build its own starships. I do not think any early colony would get that done before Earth sends another mission, at least within the first 25 light years, perhaps even the first 100 or more. So I am assuming every settlement in this range launches directly from Earth, with few true way stations, except maybe binaries or Proxima Centauri. I think we would build a lot of them en route though, peeling a ship off from a fleet to settle some rogue planet direct along that general pathway, and establishing a base there. It's a good thing to do with folks in the fleet who may have changed their mind and want to go home, as is also a refueling stop, or who are clashing with the main leadership. These are very long voyages that represent entire cultural epochs, actual civilization on the move, not just long trips before setting up a civilization. My own guess is that we will see settlement of Alpha Centauri in the 23rd century. It could be sooner, in the 22nd, but if so, that implies we tackled space much more robustly and that everything nearby gets settled quickly thereafter. After that first mission arrives and succeeds, within a generation or two, you likely see a push to settle everything in reach, on top of a solar system that already has a few hundred off-world settlements. So by the 24th century, we'll see a major ramp-up of departures, and by 3000 AD, every star within 25 light-years either has a fledgling colony or one about to arrive. Beyond this inner sphere, I tend to assume colonization expands at roughly half the speed of your fastest ships. That is, the main colonization wavefront advances more slowly than your record-setting probes, while a few very high-speed, long-haul missions head for black holes or star clusters to help them slow down and establish footholds far out in the galaxy. But that's beyond today's scope, and as you might guess, it depends a lot on available technologies. We won't find Edens, we'll have to build them, and how fast and well depends on your toolbox. We have episodes digging into more of these options in detail with more on the way. For alerts when those and other episodes drop, make sure to like, subscribe, and hit the notification bell. And until next time, thanks for watching, and have a great week.